Hi everyone. So now we are slowly, uh, gonna build up deep in topology. So if you remember, again go back to the very first lecture, we talked about we will have a set, we will give some structure on it, we will call it topology. Then the set along with that structure will be called topological space, and we will talk about some maps between them, and we will decide when two of them are equivalent. So that is what homeomorphism is. So naturally, if two spaces are homeomorphic, then they have same cardinality, right? Because there is a 1-1-on-2 map between them. But here, but this kind of property was preserved just because of the bijective thing. So similarly, like in vector spaces, when you call two vector spaces isomorphic, there are some properties which one has, then other will also have. So such things we are gonna talk about. So the very first property which we will see is connectedness. So to begin with, let me formally have this definition: topological property. So what do we mean by a topological property? Let no need to, let's define in English. I mean in language only. A property P is said to be a topological property if it is preserved under what? Homeomorphisms. Meaning, say f from x to y is a homeomorphism. So no need to begin with let x and y be topological spaces. Of course, if we talk about homeomorphism, it has to be between topological spaces. Okay? So, say x satisfies, sorry, whatever the spelling is, let me correct it. Satisfies P, some property. And this P is what topological property we are saying. Then Y must satisfy P. If P is a topological property. So one example, immediate example you have is cardinality. Yeah, it is preserved under bijection. So every homeomorphism is also a bijection, right? So example, the very first example is cardinality. Cardinality of the set X in this case, above case. So now let us move on to, something more, where we will actually make use of homeomorphism or continuity, these kind of things. So as I have titled the section connected spaces, so let us define What is a connected space? So definition. We say X along with tau is a disconnected space if. So what I am defining is disconnected. If there exists u comma v in tau, meaning open sets, such that number one, u intersection v is empty, they are disjoint. Number two, their union is X, right? Makes sense, right? If you take 2 points separately, that is your space only, just 2 points. And if you take, say, topology to be discrete topology. Okay, I want to consider this example. So, example. Oh, okay, let me just complete it. So, a space X tau is connected if it is not disconnected. Seems natural, right? Basically, you cannot write your space as union of two disjoint non-empty sets. Have I written non-empty? So let me write that also. So, because if U is empty, no, such that my bad. So I should have written it. So yeah, that's how if you remember the concept, then you can easily deduct if you are making some silly mistake in definition, which can be very serious. It can be silly, but that doesn't stop it to make uh, to maybe it can be very serious. Yeah. Okay. So let us have an example. Example. Let us just take x equal to just 2 points a, b. Say a is different from b. Okay? Now, tell me, what do you think? Is it connected or disconnected? So say just these 2 points. If I just give you these 2 points and this orange, these 2 points, is your space, you will say, oh, these points are separate. It should be disconnected. But that's not the case always. Let us see why. So for example, why you can theoretically argue why there is something tau. This topology plays a very crucial role. So say, for example, you take tau1 to be a indiscrete topology. These are the only open sets. So do you have two disjoint non-empty set such that you can write X as union of those? No, right? So X tau1 is connected. You see, a very trivial and beautiful example. But if I define tau1 to be this, phi a b a b. If you see, this is just power set of this, basically discrete topology. Then, now, is this disconnected? It is, right? So X you can write as union of singleton A, union singleton B. You see? two points. If I just draw on a plane like this, I have drawn, you may think, oh, this looks disconnected. But be mindful, there in your mind, you're already having a topology. For example, if I draw 2 points in R2, so when you look it as a subspace, there is a subspace topology. You can see if you take any finite subset of R2, then that is what? The topology will be nothing but discrete topology. So that topology you always have in your mind whenever you see two dots, one here and one there. Oh, there is a disconnection. I cannot join them. But what space you are taking, what topology you are taking is very important. So this very, very basic example tells us this thing. One of the very beautiful thing about the topology. What it seems in nature, you have to be more careful, right? In nature, as in, if I just draw a plane and ask these 2 points, then students will say, hey, if someone don't know topology, yeah, this is disconnected. But inside their mind, or they don't know it, but actually what they are doing is they are taking the subspace topology of R2 on that particular space or set of 2 points. That turns out to be discrete topology. So I hope you got my point. So this is one. Number two. See, you have X with discrete topology. Is it connected? You've seen an example. It is disconnected. But can it be connected? Think about it. Okay, let me think about these cases. If cardinality is 1 and if cardinality is bigger than 1. In this case, you will see that it will coincide, the discrete topology will coincide with the indiscrete and that space will be connected. And in this case, you will see that there will be a disconnection, meaning there will be two open sets which are disjoint, non-empty, and the union is your whole space X. Okay. Let us take one more example. I had two in mind, but I forgot. It's fine. So let us take X to be an infinite set, okay? And X with tau COF. Do you remember? Tau COF meaning X along with tau COF, co-finite. So with co-finite topology. So recall. So this is empty set along with all sets U such that X minus U, the cardinality of this set is finite. So complement finite, that's why co-finite. Okay. So, yeah, sorry, I'm having a little bit cold as always because of the weather, of course. Okay, now let us see if it is connected or disconnected. So say it is disconnected. So let U comma V belongs to tau cofinite such that U is non-empty, V is non-empty, and U intersection V is what? These are disjoint, and X is U union V. Right? So that's what you have. Now from here, or maybe from here. So what this condition will imply? If we take the complement, This will be x.
So
So meaning
x
x
minus
minus
u
u
union
union
x
x
minus
minus
v
v
is
is
what?
what?
X,
X,
right?
right?
Now
Now
note
note
that
that
cardinality
cardinality
of
of
x
x
minus u
minus u
is
is
finite.
finite.
Cardinality
Cardinality
of
of
x
x
minus v
minus v
is
is
finite,
finite,
right?
right?
But
But
this will
this will
imply
imply
cardinality of
cardinality of
x
x
is
is
finite.
finite.
This is
This
a
is a
contradiction,
contradiction,
right?
right?
We have
We have
assumed
assumed
my
my
space to
space to
be
be
infinite,
infinite,
right?
right?
So
So
this is
this is
not
not
possible.
possible.
So
So
what
what
you
you
observe
observe
here
here
is
is
this
this
x
x
with
with
tau
tau
with
with
cofinite
cofinite
is
is
connected.
connected
If
if
x
x
is
is
infinite.
infinite.
So
So
your
your
homework
homework
is
is
what
what
if
if
cardinality
cardinality
of
of
x
x
is
is
finite.
finite?
Okay.
Okay.
Another
Another
homework
homework
is
is
what
what
about
about
x
x
with
with
co-countable
co-countable
topology?
topology?
So
So
what
what
about
about
x
x
along
along
with
with
fourth
fourth
space?
space,
Basically
basically
fourth
fourth
space
space
x.
x?
I
I
have
have
defined
defined
these
these
topological
topological
spaces in
spaces
the
in the
very
very
beginning.
beginning.
So
So
I
I
request you
request you
guys to
guys to
check
check
whether
whether
these
these
are
are
connected
connected
or
or
not.
not.
These are
These are
all
all
homeworks.
homeworks.
Another,
Another,
what
what
is
is
with
with
R
R
with
with
usual
usual
real
real
line?
line?
What
What
is
is
R
R
with
with
lower
lower
limit
limit
topology?
topology?
So
So
argue
argue
if
if
these
these
things are
things are
connected
connected
or
or
disconnected
disconnected
by
by
definition.
definition.
Okay,
Okay,
I
I
hope
hope
these
these
examples
examples
are
are
more
more
than
than
enough
enough
for
for
now.
now.
We
We
may
may
see
see
many
many
more
more
as
as
we
we
proceed.
proceed.
So
So
let
let
me
me
have
have
a
a
okay.
okay.
The
The
very
very
first
first
thing.
thing.
So
So
this
this
connectedness
connectedness
is
is
a
a
topological
topological
property.
property.
Let us
Let us
see
see
why.
why.
So
So
let
let
x
x
be
be
connected.
connected.
Hmm,
Hmm,
let's
let's
write
write
like
like
this.
this.
Let
Let
x
x
comma
comma
tau
tau
x
x
and
and
y
y
comma
comma
tau
tau
y
y
be
be
spaces,
spaces,
meaning
meaning
topological
topological
spaces.
spaces.
I am
I'm
not
not
talking
talking
about
about
any
any
other
other
space.
space.
F
F
from
from
x
x
to
to
y
y
is
is
onto
onto
and
and
continuous.
continuous.
Then
Then
x
x
is
is
connected
connected
implies
implies
y
y
is
is
connected.
connected.
Okay.
Okay.
So
So
meaning
meaning
if
if
I
I
have
have
f
f
and
and
homeomorphism
homeomorphism
from
from
x
x
to
to
y,
y,
and
and
if
if
x
x
is
is
connected,
connected,
then
then
y
y
has
has
to
to
be
be
connected.
connected.
Or
Or
y
y
is
is
connected,
connected,
then
then
x
x
has
has
to
to
be
be
connected.
connected.
But
But
what
what
I'm
I'm
saying,
saying,
we
we
don't
don't
need
need
the
the
actually
actually
the
the
continuity
continuity
of
of
inverse
inverse
here.
here.
This
This
is
is
also
also
sufficient.
sufficient.
Why
Why
I'm
I'm
taking
taking
on to?
on to
Because
because
I
I
want
want
to
to
go
go
on
on
y
y
somehow.
somehow.
Okay.
Okay.
So
So
assume
assume
we
we
will
will
proceed
proceed
by
by
contradiction.
contradiction.
So
So
assume
assume
y
y
is
is
not
not
connected,
connected
if
if
possible.
possible.
Y
Y
is
is
not
not
connected.
connected.
So
So
guys,
guys,
what
what
this
this
will
will
imply?
imply?
This
This
will
will
imply
imply
there
there
exist
exists
u
u
comma
comma
v
v in
tau
tau
y
y
such
such
that
that
u
u
is
is
non-empty,
non-empty,
v
v
is
is
non-empty.
non-empty.
These
These
are
are
open
open
sets,
sets,
right?
right?
Because
Because
I'm
I'm
taking
taking
in
in
topology.
topology.
U
U
intersection
intersection
v
v
is
is
disjoint.
disjoint. I mean,
Yeah, it's
it's
empty.
empty.
And
And
y
y
is
is
what?
what?
U
U
intersection
intersection
v.
v.
Now,
Now,
guys,
guys,
what
what
is
is
f
f
inverse
inverse
of
of
y?
y?
It
It
is
is
nothing
nothing
but
but
f
f
inverse
inverse
of
of
u
u
intersection
intersection
f
f
inverse
inverse
of
of
v.
v.
This
This
is
is
what?
what?
X,
X,
right?
right? Now tell me a few things. Have I done any mistake? Yeah, there should be union. So, this also belong to tau x. This also belong to tau x. I mean, these two belongs to tau x. Why? Because f from x to y is continuous. Right? Okay. Now, so maybe, yeah, okay, fine, no issues. Now, this is x, right? F inverse of y. Okay. So, what is f inverse of u intersection f inverse of v? This is what? F inverse of u intersection v, which is f inverse of empty set. This is nothing but empty, right? And clearly, f inverse u is also non-empty. F inverse v of is also non-empty. Why? Why? This is important because u and v are non-empty. Oh, so what? Inverse image can be empty, but we have assumed f is on u. So see, we have used continuity also, we have used surjectivity also, or ontoness also. So what you are getting is x you can write as union of two open sets which are disjoint, non-empty. So this is not possible. So this implies x is not connected or disconnected. This is a contradiction. Why? Because you have assumed that x is connected. Now, I'm gonna give you one more exercise. Please try this on your own. You will easily find solution everywhere. But I don't want you guys to look into the solution. This is something you can, always do on your own. So, the following conditions are equivalent. The following are equivalent. What following are equivalent? Number one, x is connected. Phi and x are only clopin sets. Okay? Other than that, if x is connected, you cannot have a set which is both open and closed. So I can give you just, verbal justification. So if you have supposedly f which is non-empty, which is not equal to x, it's both open and closed. So f and f complement both are open, both are non-empty, both are not equal to x. What is their union? X. So x become disconnected, right? That's all. So see, the reasoning is very simple. That's why I'm leaving these things as exercise. Now this is very important. Every continuous map f from x to d and d with any space with discrete topology is constant. Constant. This is again very fun to see. So if you take any discrete space, then it will be, sorry, not 2 to the power x, it should be 2 to the power d. Right? Discrete space meaning discrete topology. So every continuous map like this is always constant. So these are the equivalent conditions I request you guys to prove. Now, how to see more and more, criterias of something being connected. So we always need, plenty of results if we have what we can apply in what situation. Sometimes it is very easy. So for example, if I ask you to show that Sn is connected. Okay. Now you will Sn n bigger than or equal to 1. This is important. So now you will think, oh my god, how to do this? Oh, it looks like connected, right? You cannot break into parts. But that's not the justification, right? Or you show these things, second, third. These can be also very difficult. So that's why if we have some more criterias to judge that something is connected, then it's an always an advantage. I'm not saying you cannot do with those things, but it might be difficult, right? So let me do two theorems and then we will actually solve this example. Let me forward the statement. Let me see. So let y alpha and some capital lambda be a family of connected subsets of X such that if you take any two distinct, then they are what? Their intersection is non-empty. Okay? Of course, yeah. Okay, if you take any two, then their intersection is non-empty. Then union of y alpha is also connected. Now here we will see how we can use the equivalent criteria which I have mentioned above for the connectedness. So let us use third. So to prove third, what we can do? Let's see. Oh, I mean, yeah, we will prove that. Okay, so let D be a discrete space. Okay. To show f from union y alpha to D is constant, right, guys? That's what we have to show. So let us see. So note that f restricted to y alpha, just this set. This will be from y alpha to D. Okay, to show this is constant every continuous f. So I remember I have given you an exercise. Show that restriction of a continuous function is continuous. So this is continuous and y alpha is connected. So what this implies, guys, this is constant. Okay. So say f restricted to y alpha of y alpha, since this is constant, this is just say singleton sum d alpha. Alpha in capital net. Okay. Now, what you have to show? You have to show that f is constant, right? Have you used fully hypothesis? No, we just have used that y alpha is connected. So let us use that intersection thing. So for any y alpha and y beta, we know that y alpha intersection y beta is what? Non-empty. So this means there is a point. So let's call it x alpha beta. Right? So what you have is f restricted to y alpha of x alpha beta is same as f restricted to y beta of x alpha beta y, because these are restriction on the y. This set and x alpha beta belongs to both of the sets. So what you get here is, here you have d alpha, here you have d beta. So what you have shown, d alpha is equals to d beta for every alpha comma beta in capital lambda. So you see, you get that f is constant, right? Because what is f? For any point in union, it is in some y alpha and it is giving the value d alpha. What we have shown, all these d alphas are equal. So f is constant. It's a fun proof, no? I mean, I enjoyed it at least. Okay. So, I need to, yeah, let me give you an exercise. Exercise. Let me copy it what I want, because otherwise I will forget. Okay. So let C contained in X be connected, and Y alpha, like above, be a family of connected subsets in X. But I am not saying now they are pairwise disjoint or anything. The condition is such that C intersection Y alpha is non-empty for every alpha. Now can you tell me what will happen? What you can show is union Y alpha with C is connected. Okay? This is a corollary. So I will give you an hint if you want. So define Z alpha to be C union Y alpha. That's all. And this is a corollary of above. And this is very important because we are gonna use it. Okay. So let me do the another theorem which I was talking about. Theorem. So we will do this, connectedness in say 2 parts or maybe more. So yeah. So let us do this theorem. So let I is in say 1 to n are connected topological spaces. Okay, then the product of these is connected. So that is what we have to show. Okay. Now, what you can do is, okay, let me think something. Let us show for n equal to 2. How will you do for then general n? You can use principle of mathematical induction. So you have x1, you have x2. Now what I'm going to do is, so choose x1 and x1, okay? And define c1 to be, or maybe c would be fine. Let me think, C would be fine. C to be x1 cross x2.
Okay?
Okay?
Note
Note
that.
that node
C
C
intersection.
intersection.
You
You
may
may
say,
say,
if
what
if
if
x1
x1
is
is
empty,
empty?
then
Then
it's
it's
nothing
nothing,
now.
na?
It's
It's
just
just
x2
x2
only.
only.
Okay.
Okay.
What
What
is
is
C
C
intersection
intersection
with?
with?
X1
x1
cross
cross
x2,
x2,
I
I
mean the
mean the
product
product
of
of
these.
these.
This
This
is
is
non-empty,
non-empty,
right?
right?
Why?
Why?
Because
Because
x1
x1
comma
comma
x2
x2
belong
belong
in
in
both
both
of
of
them.
them.
X2 is
x2 is
also
also
non-empty.
non-empty.
The
The
spaces
spaces
are
are
empty.
empty.
It
It
doesn't
doesn't
make
make
sense
sense
to,
to,
talk
talk
about the
about the
product,
product,
right?
right?
So
So
this
this
is
is
non-empty.
non-empty.
And
And
for
for
any
any
x2
x2
in,
in,
say,
say,
x2,
x2,
the
the
C
C
intersection
intersection
x1
x1
cross
cross
singleton
singleton
x2
x2
is
is
also
also
what?
what?
Non-empty,
Non-empty,
right?
right?
So
So
now
now
what
what
we
we
will
will
do,
do,
see
see
how
how
you
you
can
can
write
write
your
your
x1
x1
cross
cross
x2.
x2.
You
You
can
can
always
always
write
write
it
it
what?
what?
x1
x1
cross
cross
singleton
singleton
x2,
x2.
x2
x2
varies
varies
over
over
x2,
x2,
right?
right?
And
And
what
what
is
is
this?
this?
Can you
Can you
write
write
like
like
this?
this?
Union
Union
C?
C?
Think
Think
about
about
it.
it.
And
And
by
by
above
above
lemma,
lemma,
or
or
sorry, corollary
corollary
we
we
call
call
it,
it,
right?
right?
By
By
above
above
exercise,
exercise,
because I
because I
have
have
given
given
exercise.
exercise.
What you
What you
get?
get?
You
You
get
get
this
this
is
is
connected.
connected.
So
So
it's a
it's a
bit
bit
tricky,
tricky,
but
but
it's
it's,
it's
it's
again
again
a
a
very
very
good
good
application.
application.
So
So
now
now
we are
we are
in
in
position to
position to
show
show
that
that
what?
what?
Sn,
Sn,
where
where
is
is
Sn?
Sn?
Sn
Sn
is
is
connected.
connected.
So
So
let
let
us
us
call
call
this
this
star.
star.
So
So
let
let
us
us
finally
finally
show
show
this.
this.
So
So
let's
let's
show
show
Sn
Sn
is
is
connected,
connected,
provided
provided
n
n
is
is
bigger
bigger
than or
than or
equal to
equal to
1.
1.
Now,
Now,
see,
C,
note
note
1.
1.
If you
If you
remove
remove
1
1
point
point
from
from
Sn,
Sn,
0,
0,
0,
0,
1.
1.
This is
This is
open,
open,
right?
right?
If you
If you
remove,
remove,
no
no
need of
need of
opening,
opener
actually, yeah.
actually, yeah.
So
So
this is
this is
this.
this.
And
And
let's
let's
take
take
V,
V,
V
V
to
to
V.
V.
Ah,
Ah,
I'm
I'm
sorry
sorry
for
for the
so
so
many
many
colors.
colors.
V
V
to
to
V,
V,
Sn
Sn
minus,
minus
say.
say.
Basically,
Basically,
I'm
I'm
removing
removing
north
north
and
and
south
south
poles.
poles.
So
So
U
U
intersection
intersection
V
V
is
is
empty,
empty,
non-empty,
non-empty,
guys,
guys,
right?
right?
And
And
what
what
is
is
this?
this?
Do you
Do you
remember
remember
stereographic
stereographic
projection?
projection?
See,
See,
everything
everything
what we
what we
have
have
done, we
done,
are
we are
actually
actually
using.
using.
So
So
U
U
is
is
homeomorphic
homeomorphic
to
to
Rn.
Rn.
V is
V is
also
also
homeomorphic
homeomorphic
to
to
Rn.
Rn.
This
This
is
is
connected.
connected.
This
This
is
is
also
also
by
by
above
above
theorem.
theorem.
And the
And the
exercise I
exercise I
have
have
given you
given you
show
show
that
that
R
R
is
is
connected,
connected,
right?
right?
So
So
intersection
intersection
is
is
given,
given,
so
so
it
it
means
means
U
U
union V
union
is
V is
connected.
connected.
The
The
first
first
theorem we
theorem we
have
have
done,
done,
the
the
theorem
theorem
before the
before the
above
above
theorem.
theorem.
So
So
this
this
implies
implies
Sn
Sn
is
is
connected.
connected.
So you
So you
see,
see,
sometimes
sometimes
it
it
is,
is, very useful to have,
more
more
and
and
more
more
results
results
like
like
this.
this.
Okay,
Okay,
so I
so I
was
was
looking
looking
uh,
uh,
the
the
time,
time,
so we
so we
can
can,
also
also
do
do
one or
one or
two
two
applications.
applications.
So
So,
application.
application.
So
So
this
this
is
is
basically
basically
your
your,
we
we
call
call
it
it,
intermediate
intermediate
value
value
theorem,
theorem,
generalization,
generalization,
intermediate
intermediate
value
value
theorem.
theorem.
So
So
let
let
X
X
be
be
connected
connected
and
and
F
F
from
from
X
X
to
to
R
R
be
be
a
a
sorry
sorry,
continuous
continuous
map.
map.
So
So
R
R
have
have
a
a
specified
specified
topology.
topology,
I
I
have
have
tell
told
you
you
many
many
times.
times,
Then
then
it
it
is
is
just
just
the
the
real
real
line R.
line.
So
So
what
what
you
you
have
have
to
to
show?
show?
So
So,
okay.
okay,
So
so
I
I
mean,
mean,
what's
what's
the
the
statement
statement
is?
is?
So
So
if
if,
let us
let us
see.
see,
If
if
I
I
have
have
this
this
sum
sum
f
f
small
small
x
x
less
less
than
than
c
c
less
less
than
than
fy,
fy,
x y
xy
in
in
x,
x,
basically
basically
between
between
any
any
two
two
values
values
of
of
f,
f,
it
it
assumes
assumes
every
every
value.
value.
That's
That's
what
what
I'm
I'm
gonna
gonna
write.
write.
Then
Then
there
there
exists
exists
some
some
z
z
in
in
x
x
such
such
that
that
f
f
of
of
z
z
is
is
c.
c.
So
So
that
that
is
is
what
what
the
the
very
very
first
first
application
application
we're
we're
gonna
gonna
do.
do.
Okay,
Okay,
now
now proof.
okay.
Okay,
So
so
x
x
is
is
connected,
connected,
right?
right?
This
This
implies
implies
f
f
of
of
x
x
is
is
connected,
connected,
right?
right?
Image
Image
is
is
connected.
connected, right?
Now,
Now,
so
so
say,
say,
see,
see,
f
f
of
of
x
x
is
is
connected,
connected,
and
and
this
this
is
is
connected.
connected.
I
I
can
can
give you
give
an
you an
exercise
exercise
here.
here.
Subset
Subset
of
of
R
R.
show
Show
fx
fx
is
is
in
in
interval.
interval.
So
So
if
if
fx
fx
is
is
an
in
interval
interval
and
and
c
c
belongs
belongs
to,
to,
then
then
so
so
fx is
fx
an
is an
interval.
interval.
What is
What
the
is the
definition
definition
of
of
an
an
interval?
interval?
If
If
any
any
two
two
points
points
which
which
belongs
belongs
there
there
and there
and there
is
is
any
any
other
other
point
point
which
which
lie
lie
between
between
them.
them.
So
So
this should this
this
implies
implies
c
c
should
should
also
also
belong
belong
to
to
f
f
of
of
x.
x.
That's
That's
all.
all.
So
So
this
this
is
is
again
again
an
an
exercise.
exercise.
Actually,
Actually,
this
this
is
is
not an
not an
exercise.
exercise.
How
How
will you
will you
show
show
that
that
R
R
is
is
connected?
connected?
So
So
something
something
similar
similar
you
you
have to
have
do
to do
here.
here.
So if
So
you
if
have
you have
shown R
shown
is
R is
connected,
connected,
then the
then the
interval is
interval is
also
also
very
very
easy.
easy.
Okay,
Okay,
because
because
R is
R is
itself
itself
an
an
interval.
interval.
Open
Open
interval
interval
minus
minus
infinity
infinity
to
to
infinity.
infinity.
Okay,
Okay,
and
and
fx
fx
cannot be
cannot be
constant
constant
because
because
I
I
am
am
already
already
taking
taking
2 points
2 points
there.
there.
Okay,
Okay,
if it
if it
is
is
constant,
constant,
then
then
everything
everything
is
is
fine.
fine.
So
So
then
then
you
you
can
can
have
have
various
various
corollaries
corollaries
of the
of the
intermediate
intermediate
value
value
theorem
theorem
that I
that I
am
am
not
not
doing.
doing.
And
And
so
so
what
what
is
is
my
my
plan?
plan?
So
So
plan
plan
is
is
for
for
the
the
next
next
video,
video,
more
more
properties
properties of connectedness and product of connected spaces. Spaces is connected. That's what we are gonna prove next time. At least this. So yeah, and some examples also. So I think this is sufficient. So this is what we are gonna see in the next video. So some more properties in the theorem product of connected. Note that what we have proved is just for finite product, right? Yeah, finite product. But I'm writing their product. So meaning arbitrary product. So yeah, thank you very much.